Welcome back, Design Junkies, to Mechanical Engineering Made Simple.
Today, we are taking a deep dive into an industry that, most people probably associate with forestry and just basic manufacturing, pulp and paper.
Right.
But we are skipping the trees and the newsprint to look directly at the hidden, hardcore mechanical engineering required to process what is essentially liquid wood.
That is the perfect way to put it. I mean, you, the listener, probably interact with this industry multiple times a day. Think packaging, hygiene products, even special industrial filters.
Oh, absolutely. This is a massive global operation. In the year 2000 alone, our sources indicate the industry produced 188 million metric tons of pulp.
And that all has to be mixed. But here's the thing that our sources really highlight: managing this liquid wood fiber is it's just vastly more complicated than mixing water.
It's a different universe. We're talking about engineers constantly fighting against some really strange physics, like overcoming yield stress and avoiding catastrophic shaft vibration, just to keep a mill online.
Okay, that sounds less like a simple mixing problem and more like a battle against rheology. Let's unpack the physics of this wet fiber.
To start, you really need the chemical context. Pulp processing, it often begins with what's called the craft process.
And the goal there is to separate the wood fibers from the lignin, right? The stuff that holds the wood together.
Exactly. And that separation requires cooking the wood chips in white liquor, which is this alkaline solution of sodium sulfide and sodium hydroxide.
And once the fibers are liberated, you're left with this spent cooking liquid, black liquor.
You got it. And mixing is critical there, too, for environmental and safety reasons. You need to oxidize that black liquor before chemical recovery, which prevents the release of, toxic hydrogen sulfide gas.
So right from the get-go, these systems are operating in some seriously harsh chemical environments.
Very harsh. But the core mechanical headache isn't really the chemistry. It's the fiber itself. If you look at the raw material, a typical softwood trachite is long, maybe 3 to 7 millimeters in the tree.
And even after the craft process, they're still pretty big.
They're still sizable, yeah. Typically 1.9 to 2.4 millimeters long. And when you put those long fibers into water, they don't act like sand in a bucket.
They act like a net.
A net is a perfect analogy. The individual fibers are suspended, but they form these coherent, interconnected systems called flocks.
So they all just tangle up.
Instantly. Imagine you threw a whole bunch of wet, cooked spaghetti into a tank and tried to stir it. That tangled network gives the entire pulp suspension mechanical strength. Before you can do anything with it, pump it, mix it, you have to apply enough force to literally tear that network apart.
That's fascinating. So it behaves like a solid, despite being mostly water. This brings us to a fundamental concept: consistency. Or mass concentration.
Consistency is everything. Engineers categorize it. Low consistency is under 4% fiber. Medium, which is the sweet spot for a lot of processes, is between 8 and 16%. And high consistency is anything above 20.
And here's the counterintuitive aha moment our sources really emphasized. Let's take medium consistency pulp, say at 10%.
Right.
Mathematically, that material is 90% water by mass, yet it exhibits solid-like behavior.
That is the defining engineering challenge of this entire industry. Because of the strength of those fiber networks, the flocks, the suspension, develops a yield stress.
Like ketchup in a bottle.
Exactly like ketchup. You shake it, you tap it, nothing moves until you hit a certain force threshold, and then whoosh, it all flows. Pulp is similar, but way more extreme. Motion cannot start until the force applied overcomes that internal yield stress.
And I'm guessing that yield stress climbs dramatically as you add just a little more fiber.
It increases exponentially with concentration. So a mill running at 12% consistency requires significantly more robust, higher torque equipment than one running at 8. You are literally designing hardware to stir a semi-solid gel.
And this mechanical complexity isn't just an engineering puzzle. It has massive bottom-line impacts. I saw a great example in the sources about the chemical stages.
On bleaching, you mean?
Yeah. Improving the quality of the mixing can dramatically reduce how much chemical you have to use.
It's a direct trade-off. Better mixing means better contact, which means better reaction efficiency. For a big 1,000-ton-per-day mill, our sources indicate that optimizing chlorine dioxide use, just by mixing better, could save 1.4 million Canadian dollars annually.
Wow. When you see figures like that, the incentive to get the mechanical design absolutely perfect is immense.
You bet it is.
Okay, so we've identified the bizarre fluid dynamics.
Yeah.
Now let's talk about the muscle, the hardware. The industry needs a really diverse mixing toolkit, doesn't it?
It has to be. You're handling everything from those viscous yield stress fluids to, aggressive high-shear dispersions. The mixers are always task-specific.
So for that thick, non-flowing stuff.
For that, you need mixers that move the entire tank. This means close clearance impellers like helical ribbon or anchor styles. They often span 85 to 95% of the tank diameter.
And they need massive torque at really low speeds.
Exactly, to prevent the material from just spinning around with the shaft like a solid block.
Okay, and what about the flip side? What if you need to violently break up aggregates, like for preparing coatings?
Then you need high-shear mixers. It's the opposite design philosophy. They use tiny impellers, maybe 10 to 20% of the tank diameter, running at incredibly high speeds, up to 3,600 RPM.
And they use designs like a rotor stator.
Yep. A spinning inner element passes closely by a static outer element, generating these extreme localized shear forces that just obliterate lumps.
And then there's the quiet hero, the static mixer.
Ah, yes. The static mixer. 0 moving parts. It looks like a set of fixed blades inside a pipe. All the mixing energy comes from an external stock pump forcing the fluid through it.
So it just uses pressure drop and turbulence.
All without a motor or a shaft seal. It's pretty clever. The energy dissipation is around 0.03 megawatts per cubic meter.
So no matter the type, the prime mover is the electric motor. And engineers use these NEMA design codes, -B, C, or D, to specify them.
Right, and Design B is the typical choice for mixers. It gives you normal starting torque characteristics. What that means, practically, is it can handle that initial heavy load to overcome the yield stress without drawing excessive current.
Now, speaking of power, the sources stress that impeller power is extremely sensitive to speed. Why is that relationship so extreme?
It's a cube function in turbulent conditions. The power required is proportional to the cube of the impeller speed.
Wait, hold on. So if you double the shaft speed, say from 100 to 200 RPM, you suddenly need 8 times the power.
8 times, that's right. It's due to the exponential increase in drag and fluid friction.
That explains why the electrical system design is so critical. Standard AC motors are locked to the frequency, right? 1800 RPM for 60 hertz, 1500 for 50 hertz.
Precisely. And that sensitivity is why the industry has moved away from old multi-speed motors to modern variable frequency drives, or VFDs.
So you can finely tune the speed.
You can tune it exactly to the state of the pulp. Instead of that huge 8-to-1 power jump, a modern VFD can offer an incredible 64-to-1 power range.
That's amazing control, but you still have to get that speed down. Motors run around 1800 RPM, but the mixers are, what, 30 to 350?
Right, so you need massive speed reducers. And this is where the engineer's focus shifts from speed to torque.
Because torque is power divided by speed.
And since you're dropping the speed so dramatically, you are massively increasing the torque. That torque is the critical factor that dictates the sheer size and strength of every single mechanical component downstream. The gears, the shaft, everything.
So the mechanical integrity of that massive shaft is the next huge hurdle. It's not just a simple rotating rod, is it?
Not at all. It's in a constant battle. The shaft simultaneously endures torsion, the twisting from the motor's torque, and bending loads from the hydraulic forces of the impellers pushing through that thick pulp.
And engineers have to calculate the minimum shaft diameter to handle those combined loads. But they can't just design for smooth operation. They have to plan for disastrous scenarios.
Correct. They use something called hydraulic service factors, or FH. Normal steady state might be a factor of 1. But what happens if the mill shuts down for a week and all that fiber settles into a dense, solid block at the bottom?
You need immense force to restart it.
And that's what the service factor is for. Our sources show these factors can go as high as 5 or even 7.
7. So the shaft has to be designed to withstand 7 times the normal operating torque just for a worst-case start.
Exactly. It's a huge, expensive safety margin. But even if the shaft is strong enough, there's an even more insidious mechanical killer: vibration.
You're talking about critical speed.
The critical speed, or natural frequency, NC it. Every rotating shaft has a frequency where it wants to vibrate, like a guitar string. If your operating speed gets too close, tiny imbalances get magnified, and the shaft can vibrate itself to pieces.
I imagine that's a quick way to destroy a multi-million-dollar piece of machinery.
It is. So engineers have a strict, non-negotiable rule. The operating speed, N, must be kept 20% away from the critical speed, NC. You never operate between 0.8 and 1.2 times NC.
And how do they manipulate that critical speed? How do they move that boundary?
By changing the stiffness. They need to increase the stiffness of the shaft relative to its mass. And sometimes the solution is a little counterintuitive. They use hollow shafts, often made from large diameter pipe.
Hollow. You'd think solid would be stronger.
It increases stiffness dramatically while keeping the mass lower than a solid shaft of the same diameter would be. This pushes that critical speed higher, giving them a wider, safer operating window.
Okay, so you've contained the vibration. The final mechanical challenge is the seal, where the shaft passes through the tank wall. I assume that's tough.
It's notoriously difficult. These shafts are long, so they naturally have high deflection and run out of wobble. We're talking up to 0.38 millimeter.
That's way more than a standard pump seal could handle.
Way more. You've got this massive shaft whipping around slightly inside the seal housing, so you can start simple with a stuffing box seal.
Which is basically just compressed rope. Right.
Pretty much. It's simple and cheap, but it will always leak a little, either liquid or vapor, and if you're dealing with that hazardous white liquor, any leakage is unacceptable.
So for real containment, you need the double mechanical seal.
That's the industry standard for safety. You have two sets of precision seal elements separated by a chamber filled with a pressurized barrier fluid.
And that fluid does two things.
It lubricates the seal faces, and crucially, it acts as a firewall. The pressure ensures that if anything leaks, it's the non-hazardous barrier fluid, not the aggressive process chemical.
And they're innovating even beyond that. I read about seals that don't even touch.
Absolutely. Advanced designs like gas barrier seals use nitrogen. They machine these tiny micro grooves into the seal faces, and when the shaft spins, it generates a pressure cushion, a non-contacting gap.
So the theoretical life is infinite.
Or close to it. The ultimate solution is a magnetic drive, which transmits torque through a solid wall, eliminating the rotating seal entirely. But they're limited by size and cost.
That is an incredible progression of ingenuity just to keep liquid wood inside a tank.
And that brings us to the final hurdle, the invisible killer in material science, corrosion fatigue.
This is where the harsh chemistry meets the mechanical stress of the rotating shaft.
And it's not just corrosion, and it's not just fatigue, it's the destructive combination of the two acting together.
How does that work?
The cyclic stress from rotation opens up microscopic cracks on the surface, and the corrosive fluid immediately attacks that fresh, exposed metal, propagating the crack deeper. This combined action is far, far worse than either one acting alone.
And this failure often starts with microscopic pitting, especially in the chloride-rich environments of a pulp mill. So how do engineers screen materials for that?
They use empirical formulas, mainly the Pitting Resistance Index, or PI. It's a screening tool that weighs the chemical composition of the steel. It heavily credits elements like chromium and especially molybdenum.
So a higher PI means better resistance.
Much better. But the core difficulty is the duration. These mixers are high-cycle machines. They might endure 10 to the power of 9 to 10 to the power of 11 cycles over a 10 or 15-year life. You can't test that in a lab.
It's just impractical.
It's impossible. So engineers have to get predictive. They use models based on short-life data SN curves, stress versus cycles to failure, and they mathematically extrapolate that out to predict long-life performance.
And since they're predicting performance decades out, I assume they need a massive safety cushion on that prediction.
A huge one. They often apply what's called the FLEB, or Fatigue Life Extrapolation Lower Bound Correction Factor. It's a very conservative correction that basically says, even if our model is statistically wrong, we're designing to the absolute safest, lowest end estimate to prevent failure.
And this drive for multi-decade durability against both chemicals and stress is what pushes them to use those exotic, expensive alloys.
That's exactly why you see a reliance on duplex stainless steels like alloy 2205 and even super austenitic stainless steels with up to 6% molybdenum, just to fight off that initial pitting that kicks off the whole corrosion fatigue process.
It is truly astonishing that something as necessary and seemingly mundane as paper relies on mechanical systems designed to withstand solid-like flow, calculate shaft diameters to handle worst-case scenarios 7 times the normal load, and engineer materials to survive corrosive stress for over a decade.
We covered a huge amount of ground today. I mean, we learned that efficient mixing isn't just a small boost, it's a massive cost reduction. And that every single component from the gearbox to the seal has to compensate for the just plain weird rhinology of wet wood fiber.
So we've seen that mechanical safety requires these huge investments, complex seals, high alloy shafts, massive service factors. And this is all balanced against the operational savings from better mixing. So given that constant trade-off between higher mechanical cost and higher process efficiency, consider this. Where do you think future innovation in this industry should focus, maximizing efficiency with existing, reliable designs, or prioritizing the development of entirely new, cheaper, more durable materials to reduce that mechanical cost ceiling?